Hello, everybody. Okay, so in the last lecture, we were talking about uh, Isaac Newton and the the codifying of ideas about motion and gravity, and how these principles of physics work in the abstract, in general. I shouldn't say in the abstract, but in general. How does this work? How do we use that to understand things like the behavior of planets? That's what we're going to talk about right now. Um, Before we get there, though, we need to do a little bit of a history lesson because how we talk about the motion of planets has some historical baggage to it. It has some historical quirks to it. And so it's worth keeping this in mind in order to understand why we talk about planets in the way that we do. So remember way back when we were talking about parallax. That parallax, the phenomenon of parallax, was discovered by the ancient Greeks, and they used parallax to do a lot of things, like figuring out the distances to mountains by using the parallax of the mountain. Um, and at the same time, in ancient Greece, there was a debate about what is the structure of the universe. Does the sun go around the Earth, or does the Earth go around the sun? And there were groups of uh, I guess you could call them scientists, although the term scientist hadn't been invented yet. They were philosophers, right? Groups of philosophers arguing one way or the other. The Earth, the Earth is at the center of the universe, and the sun goes around the Earth, or the sun is at the center and the Earth goes around the sun. And they thought, well, if the Earth is moving, then we should see the parallax of stars. If the Earth is moving through space, then all we've got to do is watch some stars, and if those stars move back and forth with parallax, then we'll know the Earth is moving, and if the Earth is moving, then we'll know the Earth is going around the sun, and not vice versa. And then they ran this experiment. They watched the stars, and they saw no parallax. Right? Today we have the hindsight to know stars are much, much farther away than the Greeks imagined. And because stars are so far away, you can't observe the parallax of stars with the naked eye. Right? Stars' parallax is measured in arc seconds, and one arc second is way too small for the naked eye to see. So the Greeks came to the reasonable conclusion that if we don't see the parallax of stars, then the Earth must not be moving through space. And if the Earth isn't moving, then the Earth must be sitting still at the center of the universe, and everything revolves around the Earth. Right? They were wrong, but they were wrong for all the right reasons. Right? They came up with a reasonable conclusion. And so for the next 2,000 years, people people read the writings of astronomers from back in ancient Greece, and people like Aristotle wrote down, this is why we know that the Earth is the center of the universe, because we don't see the parallax of stars. And so for 2,000 years, anybody interested in, hey, why do we think the Earth is the center of the universe? You could read Aristotle's book about it, and you could compare Aristotle's writings to your own observations, and people would go, oh, yeah, no, he makes a good point. I don't see the parallax of stars either. So I guess Aristotle is right. I guess the Earth is the center of the universe, and everything revolves around the Earth. Right? That was the conclusion they came to based on the evidence that they had at hand. And so they thought that everything revolved around the Earth, not just the stars, right? That they didn't just think that there was a celestial sphere circling the Earth, but that the sun, the moon, the planets, everything revolved around a stationary Earth. And pretty quickly, they realized we got one problem with this. When you watch the sun and the moon are always moving eastward around the sky. Relative to the background stars, the sun, the moon, the planets, they all move along the ecliptic, and every day the moon moves eastward from right to left around the ecliptic. And every day the sun moves a little bit eastward around the ecliptic. And every day the planets move every day the planets move eastward, except when they don't. Because most of the time the planets move across the sky eastward, 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 but every once in a while, every few years, the planets would slow down, move backwards, which is to say westward, and then they would slow down again and start moving eastward again. Well, that's a weird problem, right? Everything else, the planets, the sun, sorry, not the planets, the sun, the moon, everything moves relative to the celestial sphere eastward. Why are these planets making this little loop-de-loop? No good answer for why, right? This, by the way, when the planets slow down, move westward, and then keep going eastward again, this is what's called the retrograde loop, or the retrograde motion of planets. The word retrograde just literally means backwards. So every once in a while, every couple of years, the planets would stop, move backwards, stop, and then move forwards again. Why? That's weird, right? And like I said, this problem, this question, lasted for 2,000 years. And in 2,000 years, people came up with some pretty decent ideas. People came up with lots of ways to sort of modify the idea that the Earth was the center of the universe to explain the retrograde loops of the planets. And they did a pretty decent job, right? They really fine-tuned this idea so that it at least they had a way to predict the motion of planets, even when they would be going backwards. But they never had a good answer as to why. Why do the planets go retrograde? Why don't they circle the Earth eastward every day like the sun does? Right? There was never a good answer as to the why. But it's hard to, after 2,000 years, they had some very good models to say, well, yeah, no, it's, people like Ptolemy. Ptolemy was a Greek in the 2nd century, and Ptolemy said, well, yeah, no, the planets, I guess there's just something about the planets that they occasionally make these loop-de-loops. Ptolemy said, hey, I've got a really good equation, I've got a really good model to say how the planets move in these loop-de-loops. No answer as to why the planets make the loop-de-loops, but just a good equation to say, well, at least now we can predict how the planets are going to move next week, next year, etc. Right? And that pacified people for, well, about 2,000 years. Right? So after 2,000 years, now let's jump over to the 16th century. After 2,000 years of tweaking and fine-tuning and nudging the idea that the Earth was the center of the universe, they had a model. They had some equations that worked really, really well. They never explained why the planets move the way that we see them, but they had some good equations to describe how. And that pacified people for a while. So flash forward. In the 1500s, mid-1500s, I want to say, a Dutch astronomer named Nicholas Copernicus realizes, actually, you can explain the retrograde motion of planets. All you got to do is say that the Earth and all the planets are orbiting around the sun. Let's say, if the Earth and Mars, in this case, if they're both orbiting the sun, then when Earth is here, then from Earth's point of view, Mars will look like it's in front of those stars. And then as Earth and Mars move to here and here, then Mars looks like it would move here. So there you go. Mars is moving eastward like it normally does. And then Copernicus said, but when they come into alignment, as the sun, Earth, and Mars are coming into alignment, Earth is getting ready to pass Mars. And then as Earth passes Mars, Mars looks like it's going to fall behind. That's the retrograde motion. And then as they come out of alignment, Earth and Mars just keep on going the way they're already going, counterclockwise around the sun, and then Mars would go back to its normal eastward motion. Right? Copernicus says you don't need to invent complicated equations and complicated loop-de-loops. All you got to do to explain the motion of planets is say that we're all going around the sun. And specifically, Copernicus said that the planets orbit the sun in circular orbits, that everything is orbiting the sun in a circular orbit. It's just at different distances, and that's why, from Earth's point of view, we see the planets moving normally and then moving retrograde and then back to normal. That the retrograde motion happens because inevitably the planets are going to come into alignment with the sun, right? And then inevitably the planet will look like it's moving backwards. Not because the planet is moving backwards, but because the Earth is passing the planet. And Copernicus publishes his book. Copernicus basically publishes a book saying, isn't this a simpler explanation? Isn't this more elegant? Isn't this more beautiful? You don't need to kludge together some complicated equations to say that the planets are making loop-de-loops for no reason, which is what people had been doing for over 1,000 years. All you need to do is say, no, we're all just going around the sun. Isn't that nicer? Isn't that a nicer explanation? The problem is, Copernicus had no proof. Copernicus's book, Copernicus's argument was basically, isn't this nicer? Isn't this simpler? Isn't this more elegant? The problem is, people had been using Aristotle and Ptolemy's idea for the loop-de-loops for 2,000 years. People had been tweaking and fine-tuning and improving the predictions for the motion of the planets using the idea of the loop-de-loops for 2,000 years. And so the old way of doing things, it worked really well. It was very accurate. It accurately explained the motion of planets. Copernicus comes along and says, no, the planets are making circular orbits around the sun. That explains the retrograde motion. And yes, it did explain the retrograde motion, but it was less accurate, right? Copernicus's model didn't explain how the planets actually move across the sky as accurately as the Ptolemaic idea did. I mean, this kind of gives a good illustration, right? Copernicus says, no, the planets should move in this S shape, but then actually the planets move in this loop shape to sort of illustrate the point, right? And so even if you read Copernicus and you thought he was onto something, even if you read Copernicus's book and you said, oh, this is nice, it's simpler, it's more elegant, but planets don't move like this. We see planets moving like that. So how can you explain that? The problem is, right after Copernicus published his book, he died. And so, I should say, Copernicus died, then his book ended up getting published. So Copernicus was not alive to find the proof that the Earth goes around the sun, not the other way around. So even people who thought he was onto something, even the people that thought that the Earth does go around the sun, had to admit, oh yeah, you've got a nice idea, but it doesn't match the way we actually see the planets move across the sky. So where's the proof? Right? Copernicus has the right idea. He just needs the improvement. Copernicus needs to improve his ideas to actually match the way planets really move around the sky. Copernicus was dead, and so his work ended up getting picked up by other astronomers. So if we jump forward a few more years, two of the big names, not the only two big names, obviously, but two of the big names that come up next are Tycho Brahe and Johannes Kepler. Tycho Brahe was not an actual astronomer. Tycho Brahe was a rich nobleman, and he wanted to make astronomy his hobby. Tycho Brahe basically he had enough money and free time to say, hey, he read Copernicus and he thought, Copernicus is onto something. Somebody really should find the proof that he's right. And so Tycho Brahe said, well, hey, I've got money and nothing but time on my hands. I'll do it. So Tycho Brahe hires a bunch of assistants and he builds a building on his land to make measurements of the motion of the planets. And so he did this. Tycho Brahe and his assistants went out every night for 25 years. And every night they went out and measured by naked eye. Telescopes still haven't been invented yet. But every night, by naked eye, they plotted and measured the positions of the sun, the moon, the planets, some stars, so that after 25 years, Tycho Brahe had volumes and volumes and volumes of numbers, just book after book, full of the raw measurements to show how the position of the planets changes night after night after night for decades. The problem is, Tycho Brahe didn't know what to do with it. Right? Tycho Brahe was an amateur. He was a dilettante. So Brahe went to Germany. Brahe was, I'm going to say Danish, I think. I'm remembering that correctly. Tycho Brahe was Danish, but he went to Germany and he hired, fresh out of college, he hires this, Kepler went to school to be a priest because, the church ran all the universities at the time, right? So basically anybody going to university was studying to be a priest. But so Kepler studied to be a priest, but also he took a lot of classes in math and astronomy. And Tycho Brahe hires him to say, hey, you're good at math, you're good at astronomy, I've got some data I need analyzed, I'm going to hire you. And Kepler said, a paycheck does sound nice. Okay, fine, I'll take the job. So then, slowly but surely, they get down to work. After a few years, Tycho Brahe dies, not at an old age. He dies of illness, and Kepler, being his assistant, his main assistant, Kepler gets the job. Kepler gets the promotion, I should say. He's now the new royal astronomer for the King of Denmark. Nice thing to put on your business cards, I suppose. And then Kepler really can get down to work. And Kepler, he starts working with Mars because Mars moves fastest, and so it's easiest to study the motion of Mars. And he starts with the data from Mars, and he watches, much like this, watching the changing position of Mars month after month after month after month after month for years. And he's trying to take these raw measurements for how Mars moves around Earth's sky, and he's trying to make them fit with, can I show that Earth and Mars are orbiting the sun? And can I do this well enough? Can I do this accurately enough to show that that the motion of Mars is actually explainable if Mars and Earth go around the sun? And he's pounding away at these numbers for 8 years. For 8 years, he can't make the numbers make sense. He can't show how the planets can orbit the sun in a way that actually explains the motion of Mars the way we actually see it. The math just doesn't add up. This is basically the world's worst accounting homework. His boss gave him a giant spreadsheet and said, figure it out, and then the boss died. And left Kepler to the job. After years, Kepler figured out that he had been making one basic assumption. And this is the same assumption that Copernicus made. Copernicus said that the planets orbit the sun in circular orbits, perfectly circular orbits. And Kepler couldn't make it work. So eventually Kepler said, well, what if the orbits of the planets aren't circles? What if they're ellipses? And then everything started working out. Right? As soon as Kepler allowed for the orbits of the planets to not be perfect circles, then the measurements started clicking into place. Everything started making sense. And so Kepler was able to figure out how the planets go around the sun, and he codified this into 3 laws. So here we got three new laws, 3 more laws. These are what are called Kepler's 3 laws of planetary motion, right? Kepler came up with 3 principles to describe how the planets orbit the sun. He started off publishing his first book to say, hey, okay, here are the rules for how Mars goes around the sun. And then after Mars made sense, then he expanded to the rest of the planets. But they all work according to the same 3 laws. Okay, before we get into this, let me repeat what I just said a second ago. Kepler's laws describe how the planets move around the sun. They don't actually explain why the planets orbit the sun. Okay? Now, we know from the last lecture, why do planets orbit the sun? What's keeping the planets in their orbits around the sun? Well, gravity does. Gravity and Newton's laws of motion, right? Gravity and Newton's laws of motion explain why planets orbit the sun. The problem is Newton hasn't been born yet. We're still at the point in history before the birth of Isaac Newton. So nobody understands why the planets orbit. We wouldn't figure that out until Newton. Kepler's laws describe how the planets go around the sun. They don't explain why. Right? And so I'm saying this because Kepler's laws are convoluted. Right? Kepler's laws of planetary motion they're a little dense. Okay, so we're going to unpack this. We're going to unpack this, slowly, so that hopefully it makes some sense. I just want to give you the heads up that yes, it's convoluted because Kepler didn't know why the planets move the way they do. He's just describing how they do it based on the way we actually see planets move across the sky. Okay? Okay. Kepler's first law is that the orbits of the planets are ellipses, specifically with the sun at one focus. What does that mean? We'll unpack that in a second. Kepler's second law says that if you draw a line between a planet and the sun, that line will sweep out equal areas in space during equal intervals of time. Okay, this is what I mean by convoluted, right? Okay, let's unpack this here, though. All right. If it's been a little while since you studied ellipses in geometry class, it certainly has for me. You could probably use a little bit of a refresher. Okay, what is an ellipse? An ellipse is an oval, right? Specifically, it's an oval that is defined by having these 2 fixed focus points. There are these 2 fixed points in space, and then if I take, let's say, 2 nails and a loop of string, and if I take a pencil and pull that string taut so that this string makes a nice tight triangle, then if I sweep this pencil out in all directions, if I pull on the pencil to keep that loop of string taut, and if I sweep the pencil out, that pencil will draw out this ellipse. All right, so an ellipse is an oval that is defined by where are your 2 focus points and how big is your loop of string. If you knew where your focus points were and how big your loop of string was, you would know exactly what the shape of this ellipse was. Okay? So an ellipse is defined by having these 2 diameters. The long axis here is what's called the major axis. The short axis here is called the minor axis. All right? What if your 2 focus points are at the same place? What if you've got these 2 nails, but they're both at exactly the same place? Well, if your 2 focus points are at the same point, then your loop of string just goes like this, and then what shape does your pencil draw? Your pencil draws a perfect circle. So actually, a circle is an ellipse, right? All circles are ellipses. A circle is just an ellipse where the two focus points are in the same place. But if your two focus points are farther apart, then you're going to get a more elongated ellipse. The shape of an ellipse is described in terms of what's called eccentricity. So eccentricity is a measure of how elongated, how stretched out is your ellipse. If your ellipse is a perfect circle, then it has zero eccentricity. It's not stretched out at all. And then here's an ellipse where the two focus points are a little farther apart, so you've got a moderately eccentric ellipse. It's a little stretched out. If you pull those two focus points really, really far apart, then you're going to get a really strongly stretched out ellipse, so that's a high eccentricity ellipse. So eccentricity is a number that measures the elongation or the how stretched the ellipse is. Okay? All right, so let's unpack those first two laws again. All right, so here you've got the sun. Here's a planet going around the sun. All right, Kepler's first law says planets orbit the sun in elliptical orbits. The shape of a planet's orbit is an ellipse, specifically the sun, with the sun at one of the two focus points. So here's one focus, here's the other focus. The sun has to be at one of these 2 points. So the sun is at one focus. What's at the other focus point? Nothing. It's just a mathematical point in space. All right? So the planets have elliptical orbits with the sun at one focus. Kepler's second law says, if I draw a line between the planet and the sun, right? I draw this line here. If the planet moves from here to here, that line is going to sweep out this wedge, this area, this shaded area in space. All right. If the planet moves from here to here, it sweeps out this long skinny wedge in space. Right? What Kepler's second law says is that if the planet takes the same amount of time to go from here to here as it takes to go from here to here, then these two areas are swept out in the same amount of time, and therefore those two wedges have the same area. Right? Kepler's second law is usually called the law of equal areas in equal time. To give you back, right? A straight line joining the planet and the sun sweep out equal areas in equal intervals of time. So in this diagram, if the planet takes 30 days to go from here to here, and the planet takes a different 30 days to go from here to here, if those two areas were swept out in the same amount of time, 30 days, then those wedges have the same area. This short fat wedge and this long skinny wedge, they have the same total area. At which point you're probably now asking yourself, so what? What is this supposed to mean? Again, this is a little convoluted because Kepler doesn't know why the planets do this. Kepler is just describing how the planets move. So let's use a little bit of intuition here. How can it be? How can it be that a planet takes 30 days to go this distance over here, but the planet only goes this distance in the same amount of time? Well, if the planet moves this far in 30 days, and it moves only this far in another 30 days, what can we say about a planet if it moves a greater distance in the same amount of time? Things that move a great distance in a short amount of time they're moving fast, right? The planet must be moving fast over here and slow over here, right? The planet must be moving really slow because it only goes this distance in 30 days. The planet is moving really fast over here because it goes this distance in 30 days. That's why the short fat wedge and the long skinny wedge have the same area. That's the important thing to take away about Kepler's second law, right? The thing about the equal areas is, neat and all, but that's not the important takeaway. The important takeaway is planets move faster when they're close to the sun and slower when they're farther from the sun. Right? The reason why it's coined in terms of these areas is because everything is changing. As a planet goes around the sun, everything is changing. The distance to the sun is changing. The direction is changing. The velocity is changing. The speed is changing. Everything about the orbit is changing continuously, except the one thing that does not change is the area of the wedge during a fixed amount of time. So it's nice to have one thing not change. All right. The important question here, though, is the why. Why are the areas equal? Because the planet's moving faster when it's closer to the sun and slower when it's farther from the sun. Okay. A little bit more vocabulary. The perihelion is the point in the orbit where a planet is closest to the sun. So perihelion is where the planet is closest to the sun. Aphelion is the point in the orbit where the planet is farthest from the sun. So aphelion is the farthest point from the sun. The major axis is the long axis across the ellipse. The minor axis is the short axis across the ellipse, like we just saw. The eccentricity is a value that describes how squashed or how stretched the orbit is. Eccentricity is just a number. There's no units. It's just a unitless number. But that number ranges from 0 to 1. Or rather, I should be more specific. It ranges from 0 to 0.9999999. Right? If the orbit has an eccentricity of 0, that means the orbit is a perfect circle. If your eccentricity is getting really close to 1, if it's 0.9999999, then your ellipse is very squashed, very stretched out, very elongated. All right. The period of an orbit is the time that it takes for one orbit. Right? This is another important piece of vocabulary. When you talk about the orbital period, period means time. Right? The period of an orbit is the time that it takes the planet to orbit the sun once. So what is the orbital period of the Earth? Well, the orbital period of the Earth is 1 year. It takes the Earth 1 year to go around the sun. Okay, so Kepler's first two laws worked great, and then he kept on working, and it turns out he found a third law, and Kepler's third law is that there's a simple relationship between the period of the orbit and the semi-major axis of the orbit. Okay, I talked about the major axis. I didn't talk about the semi-major axis. What the heck is that? Let's go back to our drawing here. All right, the major axis is the long axis here. The semi-major axis is just half of that. Right, it's half of the major axis. It's the semi-major axis is the distance from the center of the ellipse out to the long edge. So the semi-major axis of an orbit is the distance from the center of the ellipse out to aphelion or from the center of the ellipse to perihelion. It's half of the distance from perihelion to aphelion. All right? So what? Who cares? Why are we talking about this? Well, the semi-major axis has an interesting physical significance. Okay. When you talk about the distance from a planet to the sun, the distance is constantly changing, right? Sometimes the planet is closer to the sun. Sometimes the planet is farther from the sun. You know, perihelion is where it's closest. Aphelion is where it's farthest. But if you wanted to figure out, well, okay, the distance between the sun and the planet is constantly changing, but what's the average? What's the average distance between the planet and the sun? If you average over one full orbit, the average distance between the planet and the sun is exactly equal to the semi-major axis. One of the neat results that you get when you study ellipses is that, it's complicated, right? The equation for an ellipse is complicated, and sometimes the planet's close and sometimes the planet's far. But then if you solve the problem to say, okay, but what's the average distance? All the complications cancel out, and you just get that the average distance from the planet to the sun is exactly equal to the semi-major axis. Okay? So when I say semi-major axis, all you need to think is average distance. right? The semi-major axis of a planet's orbit is just the average distance between that planet and the sun. Okay? So Kepler's third law says there's a simple, straightforward relationship between the period and the semi-major axis, or I should say the period and the distance, the average distance, right? The farther a planet is from the sun, the more time it's going to take to orbit the sun, which hopefully makes some intuitive sense, right? If a planet orbits farther from the sun, it's going to take more time to go around the sun. But specifically, it's like this, that the period squared equals the semi-major axis cubed. And this equation is simple because we're picking our units conveniently. In this equation, period is always measured in years, and the orbital distance is measured in astronomical units, right? Take the Earth, for example, right? The period of the Earth's orbit is a year. The average distance from the Earth to the sun is an astronomical unit. That's the definition of an astronomical unit. Right? That's why we made up astronomical units. We made up astronomical units to use the Earth as the basis for this equation, right? 1 squared equals 1 cubed. But it turns out that when you measure the periods for all of the planets in years, and when you measure the orbital distance, the average orbital distance, from the planet to the sun in astronomical units, p squared equals a cubed for all of the planets. Now, why is that? Why does p squared equal a cubed? Kepler didn't know why, because nobody knew why the planets did what they were doing. Kepler just said, well, this is how the numbers work, right? Based on our measurements of the sky, this is a relationship that we get. This is really handy because this is true for all planets, even the ones that hadn't been discovered yet. Right? When Kepler was working, he only studied the planets Mercury through Saturn because those are the only planets that anybody knew about back then. Those are the only planets that you can see with the naked eye. But when Uranus was discovered, you'd say, "Oh, we discovered a brand new planet. Awesome. How far away is it? I don't know." Right? You point your telescope at Uranus, you don't know how far away it is. It's just a little blue dot in your telescope. Well, but all you got to do is watch Uranus orbit around the sun for a while, and you can figure out, okay, well, I know now what the period is. And if you know what the period is, you can solve for the distance. Now you know the distance from the sun to Uranus just by solving Kepler's third law. If you know the period, you can figure out the orbital distance. Or if you know the orbital distance, you can figure out how long the planet's going to take to orbit the star, the sun, in this case. Now, today we have some hindsight, right? Today we know the reason why planets orbit the sun is because of gravity, and gravity works the same everywhere. Gravity, the gravitational force, works the same on all objects. And so these 3 laws are called Kepler's laws of planetary motion. But they're not just for planets, right? Everything orbiting everything does it according to Newton's theory of gravity and Newton's laws of motion. And so it's not just about these 3 laws don't just work for planets orbiting the sun. They also work for moons orbiting planets, or asteroids orbiting the sun, or comets orbiting the sun, or satellites orbiting the Earth, or 2 stars orbiting around each other. Everything orbits everything according to Kepler's laws of planetary motion, because those orbits are governed by gravity, and gravity works the same everywhere. So, Kepler publishes his books. He says, here are the rules for how planets orbit the sun. And people said, hey, that works really well. But why do planets orbit the sun? And Kepler says, I don't know. Nobody knows. You flash forward a few decades later, Newton comes along and says, oh, I've got a universal theory for how gravity works. And you got to imagine everybody else working in science, Newton comes up and says, oh, hey, I figured out how gravity works. And everybody said, sure you did. That's a bold claim. People have been trying to explain how gravity works for thousands of years, and then Newton strolls up and says, "Oh, yeah, I think I got this figured out. Here you go. Here you go." So obviously, the first question somebody asks him is, "Well, wait. If everything in the universe works according to this theory of your gravity that you have, then you should be able to explain why planets orbit according to Kepler's laws." Because people knew that planets move according to Kepler's laws. Kepler had figured that out decades before, but nobody knew why. So Newton comes up and says, "Oh, planets orbit because of my gravitational force, the force of gravity that I'm explaining right here." And people said, "Well, then you should be able to explain why the orbits of planets are ellipses with the sun at one focus, sweeping out equal areas in equal time. You should be able to explain why p squared equals a cubed." And Newton, actually, by the time people asked him that, Newton had already figured that out, and then he had lost the napkin that he wrote it down on. So then Newton has to, redo the math from memory, which he could do because that's a thing that Newton could do. Now we have the why, right? Now we know that planets have elliptical orbits, sweeping out equal areas because of the laws of motion and gravity that Newton had figured out, right? But Newton added one little thing, right? Remember that, I said this on the previous slide, didn't I? Pardon me, right? Planets orbit because there's this gravitational force between the planet and the sun. And the gravitational force between a planet and the sun depends on the masses of the sun, the mass of the sun, the mass of the planet, and the distance between them. Right? In Newton's equation, the orbital distance is called r, but in Kepler's laws, we call it a, the semi-major axis, right? R, a, they're both just two symbols for symbolizing the same thing, the distance from the planet to the sun. And so when Newton derived Kepler's three laws of motion using his theories of motion and gravity, he actually ended up getting this. He ended up getting that the mass m1 plus the mass of m2 times p squared equals a cubed. Because the mass is important here. The mass of the planet and the sun, that's where the gravitational force comes from. So if you're talking about two objects orbiting around each other, if you want to do the full treatment of explaining how anything orbits anything, you need to use Newton's version of Kepler's third law. But we can simplify things a little bit, right? Now, again, in this equation, the masses are in solar masses. So m1 and m2, in this equation, m1 and m2 are in solar masses. So if you're talking about the Earth going around the sun, well then m1, we'll say that's the mass of the sun. It's one solar mass. What's the mass of the Earth in solar masses? Tiny, right? Some tiny number. So in other words, m1 plus m2 is 1 plus not much. 1 plus 0 equals 1. So this, if you're talking about planets orbiting the sun, m1 plus m2 is just 1. So 1 times p squared is p squared. You've got p squared equals a cubed back again. But if you're talking about two things that aren't a planet going around the sun, then m1 and m2 might be different, and that's going to slightly tweak your equation. If you're talking about planets orbiting another star, not the sun, well, then there's no guarantee that that star is going to have a mass of one solar mass. So pretty soon, we could be talking about planets orbiting around other stars, alien planets orbiting around other stars, in which case m1, the mass of the star, we'll call that m sub s. We'll call that ms, right? ms for the mass of the star. So m1 is the mass of the star, m2 is the mass of the planet, but the mass of a planet in solar masses is effectively 0. It's so tiny. So we're just going to ignore m2, and all we have left once we've simplified this is that the mass of the star times the planet's period squared, right? The mass of the star in solar masses times the period of the planet in years equals that planet's orbital distance in astronomical units. This should be true for any planet orbiting any star. So when we start finding alien planets around other stars, we're going to have a really powerful tool for figuring out what that planet is like. Just by using Kepler's laws of planetary motion, because Kepler's laws of planetary motion hold for any planet orbiting around any star. But if you're orbiting a star that's not the sun, you do need to add that little modification that Newton figured out to take the mass of that other star into consideration. So that's going to be a real helpful instrument for us very shortly. All right. I hope this makes some sense. Have a good day, everybody.